Hi everyone, Lando Assistant here for a comprehensive, visual, and scaffolded approach to learning mathematics. This video is going to be long again because there are a lot of things that you are going to learn here. You learn what a polynomial is, how to visualize polynomials, what are the rules for addition and subtraction of polynomials, how to use manipulatives to perform addition and subtraction of polynomials. You will learn about the distributive property. You will learn how to use the grid method to multiply multinomial times another multinomial. You'll also learn about special products, the square of a binomial, the difference of two squares, the different cases for division of polynomials, up to long division of polynomials. And we'll look at some applications of this lesson also. And eventually, we are going to remove all this visualization and scaffolding so that you'll be able to perform operations with polynomials without the use of those help. So, let's get started. What's special about polynomials? Polynomials are kind of algebraic expressions that are generally easier to add, subtract, or multiply. So that's the main reason why we group together this kind of algebraic expressions. These are the easier algebraic expressions to manipulate. And this lesson on polynomial is usually your gateway to higher mathematics because it is in this lesson that you start learning about the language of algebra. So your transition from arithmetic to algebra would always be affected by how well you understand this lesson on polynomials. So what is a polynomial? Let's begin by looking at some of the examples of what polynomials are. The constant one is a polynomial. The variable x is also a polynomial. 3x is also considered as a polynomial, and a combination of 3x plus 1 is also considered as a polynomial. So, what is a polynomial? A polynomial is an expression consisting of coefficients and variables that involves only the operations of addition, subtraction, multiplication, and positive integer powers of variables. So what operation is missing here? We do not have division because when there is a variable in the denominator that is categorized as another group, which we call as the rational algebraic expressions. There are three important points that you need to remember in order to identify whether an expression is a polynomial or not. Number one, the exponents of all variables should be whole numbers. And number two, the exponents of the variables should be non-negative integers. And number three, we cannot perform division operation by variables in the polynomial. So let's have an example. Let's say x. Is x a polynomial or not? The answer is yes, because the exponent of this variable x is a whole number. 1 is a whole number. So this is a polynomial. Next, negative 2x cubed. Here we are looking at the variable and the exponent. The exponent should be non-negative, it should be whole number, and there is no division by a variable. This expression passes these three tests, and therefore, this is considered as a polynomial. Next, square root of 3x to the fifth. Again, we are looking at the variable raised to the exponent. The exponent is a whole number, the exponent is non-negative, and there is no variable in the denominator. Therefore, this is considered as a polynomial. X to the fifth. Again, the exponent of x is 1, and we are looking at this to decide whether this is a polynomial or not. Again, the exponent is 1, it's a whole number, it's a non-negative integer, and even though there is a division operation here, this division is by a constant. Therefore, this is still considered as a polynomial. But when the denominator is a variable, that is when we say that is no longer a polynomial. So all of these are polynomials. Next, if we have 6x plus 2 divided by 2, notice that we have a division operation here, this fractional bar, but the denominator is a constant. This is still a polynomial because only when the denominator is a variable when the expression is no longer considered as a polynomial. So these are the types of algebraic expressions that are easier to manipulate. Next, let's look at some non-examples of polynomials. First is, if we have x raised to 1/2, this is not a polynomial because the exponent is 1/2 and 1/2 is not a whole number. Next, 2x raised to square root of 3. So again, we are looking at this exponent. This is not a whole number, so this is not a polynomial. Next, 2x raised to negative 5. Again, this is not a polynomial because we have a negative exponent. We want the exponent to be always positive in order to have polynomials. And again, this is not polynomial. X over y. Notice that you have here division, and there is a variable in the denominator. And therefore, this is not a polynomial. 3x plus 2 over 2ab. Notice that in the denominator, there are variables a, b, so therefore this is not considered as a polynomial. Now, let's have more examples of identifying polynomials. How about 1? Is 1 a polynomial? Of course, yes. 1/2 is also a polynomial because it is a constant. All constants are in fact polynomials. Whether you have -5, 0, square root of 7, these are all constants and therefore they are all polynomials. But when -5 becomes the exponent, that's when you do not have a polynomial. When square root of 7 is the exponent, that's when you don't have a polynomial. But by itself, all constants are considered as polynomials. Now, let's have more examples. How about 3x? Is this a polynomial or not? The answer is yes, because the exponent of x is 1, it's positive, it's whole number, and there is no division by a variable. 3y squared minus 2x plus 3. Is this a polynomial? Let's look at the variables. We have y raised to the second. This passes the test. X, it also passes the test of a polynomial. And therefore, 3y squared minus 2x plus 3 is a polynomial. Another example, 3x y raised to -2. So notice that we have here x y raised to -2 in the variable parts. Because -2 is the exponent of the variable y, and we said we cannot have a negative exponent in the variables in order to have a polynomial. Therefore, this is not a polynomial. How about -2y squared plus 8 over 9x? Again, let's identify the variables. We have y raised to the second and x. There is no violation among the three tests to identify a polynomial. Therefore, this is a polynomial. How about x over 2? Again, look at the variable x. Its exponent is 1. It's positive. And the division is division by a constant. So this is not a violation. This is a polynomial. Only when this denominator is a variable, when we say this is no longer a polynomial. 3x over 8 is also a polynomial because the variable x has an exponent of 1. Square root of 2 is a polynomial because this is a constant and all constants are polynomials. 1.25 is also a constant. In decimal form, this is still a polynomial. So 2 over x plus 2, is this a polynomial or not? The answer is no because the variable x is in the denominator and that's a violation of the third test that we specify about how to know whether something is polynomial or not. 1 over x is also not a polynomial because there is a division by a variable. Y raised to 2x is also not a polynomial because the exponent contains variables. 2x cubed plus 7x squared minus 6 is a polynomial because x cubed does not violate the tests. X squared also does not violate those three tests, and therefore this is a polynomial. So let's begin now with the first operation, how to add polynomials. The rule for addition of polynomials is only like terms can be added, and that holds true also for subtraction. So what do we mean by like terms? So we can understand this better, let's begin visualizing polynomials. This is our visualization of 1. Its side length is 1 unit, and its area is therefore 1 square unit. This is how we visualize x. Its length is unknown, so that is represented by the variable x. And its width is given to be 1 unit, the same as this blue square. Now, for x squared is visualized as a square with a side length similar to this, x. So the side length is x, and therefore its area is x squared. So notice that the width of this variable x is 1 unit, and the side length of the square is x. So you have x by x to get x squared. Now going back to like terms, x and x are like terms, and you can see that when we visualize them. So this is the visualization of x, and this is the visualization of 3x. X means 1x, and 3x means 3 of the same kind, 3x. The numerical coefficient of x is 1. The numerical coefficient of 3x is 3. We are looking at this x and this x to determine whether the terms are like or not. They must be the same variables raised to exactly the same exponents. In this case, our exponents are 1 and 1. These are like terms no matter what their numerical coefficients are. And if you are going to add x plus 3x, we simply combine them and count how many of that kind are there all in all. In this case, there are 4 x's, and therefore you now say that x plus 3x is equal to 4x. That is now what we mean by saying that only like terms can be combined. Now let's have another example. Let's say we have 2x and 3x. Again, we are looking at the variables raised to the same exponents. So if we now combine 2x plus 3x, here's the visualization. Combine them. That means addition. The result is how many of that kind are there? There are 5 x's. So you now have 2 of this kind plus 3 of the same kind equals 5 of that kind. And these x are just placeholder of a known quantity. Next, x squared plus 2x squared are also considered as like terms because you have a variable raised to exponent 2 and another variable raised to the same exponent 2. So we have the same variable raised to the same exponents. The only difference is that the numerical coefficient of x squared is 1 and the numerical coefficient of 2x squared is obviously 2. To get their sum, here is the visualization. We combined 3x squared and therefore the result is 3x squared. So 1 square plus 2 squares equals 3 squares. And these squares have the same dimension, x squared. So this x squared is this 2x squared is represented by this 2x squared. And the sum would be the combination of these 3 squares. Let's have another example. Let's say x plus x squared. Here, you have a variable x raised to exponent 1. Here, you have a variable x raised to a different exponent. It's 2 now. Therefore, they are no longer considered as like terms. And so if we are going to visualize them, notice that they are different. And when you combine them, the answer is still x plus x squared. There is no more simplification that we can do. And so the answer remains as x plus x squared. This is a very important concept because many students from elementary transitioning from arithmetic going to algebra, they always expect that the answer is a single number. That is not always the case in algebra. An example of that would be this case. When you can no longer combine x and x squared, do not combine them to say 3x squared or x cubed. That's wrong. Just write the answer in binomial form like this. So sometimes your answer could consist of 2 or more terms. The only test is if the terms are no longer similar, then stop combining them. That is already your final answer. Next, if we have this x plus x squared plus 3x plus 2x squared, let's visualize them. X is this, x squared is this square, 3x would be 3 of these x's, and 2x squared would be this representation. So again, only like terms can be combined. Therefore, let's rearrange them so that the like terms are together. Like this. So x plus 3x can be combined and the result is 4x. 1x squared plus 2x squared can be combined and the result is 3x squared. And this is now the sum of x plus x squared plus 3x plus 2x squared. So again, our answer is still a binomial because we can no longer combine these two. Let's have another example. Let's say we have x plus x squared plus xy plus 2x squared plus xy plus 3. Let's visualize them. This is x squared, this is xy. And xy is a rectangle with a length of x and a width of y or vice versa. It doesn't matter whether x or y is longer than the other as long as you are consistent. Notice here that if this is our x squared, then this width here is the same dimension as this width. So this is x, this is also x, and this is a length y. Then 2x squared would be 2 squares like this, and xy would be similar to this again, and 3, we have this 1, 2, 3 smaller squares with a dimension of 1 by 1. To perform now the addition, we combine only the like terms. So let's rearrange them. So this is x, all of these are x squared, all of these are xy's, and all of these are the constants. So therefore, our answer would be x plus 3x squared plus 2xy plus 3. And that is now the sum of the expression above. Notice that our answer now has 4 terms. And we are okay with that because we can no longer combine any one of them. Then when your answer consists of 2 or more terms, by convention, we usually rearrange them in descending order of power. So from exponent 2, exponent 1 here, exponent 1 here, and exponent 0. So this is now in descending order of power. So let's have more examples of addition and subtraction of polynomials. This time, let's include subtraction. So this is again our representation of one unit. This is our representation of x, x squared, y, y squared, and xy. How about negative 1? How do you represent negative 1? We use color red to represent negative 1. It's still the same dimension, only that the color is now red. And so this is our representation of negative x, negative y, negative x squared, and negative y squared, and negative xy. When the color of our manipulative turns red, that is our representation for negative. This color coding is important because we are going to talk about what we call as the zero pair. If you have one positive that is yellow and another negative that is red, when you combine positive 1 and negative 1, the result is 0. That's why we call this as zero pair. And so when you are combining polynomials and you have one yellow and one red of the same dimension, then you can simply remove them because anyway the value would result to 0. So let's have an example. If we have x squared and you have another red negative x squared, this also forms a zero pair, and you can cancel that out later on also, as long as they come in pair. So, for example, you have 2x plus negative x squared plus negative 3y plus xy plus 3x squared. How do we visualize this now? So 2x has no problem. It's two yellow x's. Negative x squared would be red, and negative 3x would also be red, the same dimension as x, but it's color red. xy is positive, so it's yellow, and 3x squared are also yellow, 3 squares of dimension x squared, and they are all color yellow. Now, in order to simplify this, that means combine like terms, we need to rearrange so that all the like terms are similar, but not only that, we are going to remove the zero pairs. Now, this is what happens. This x and negative x form a zero pair, so we can just remove them, throw them away. Its value is 0, it will not affect the sum. The same here. This is a zero pair, so we can eliminate them. Then for x squared and negative x squared, we have one zero pair. So again, remove them. Their value is 0. And what's left is the answer. So you have 2x squared plus 1xy minus x. That would now be the answer to this problem. And when you have plus negative, we can also write that as minus of that variable. So this is now our final answer. So notice now that when you subtract algebraic expressions, it's just a matter of finding all those zero pairs. And since their combined value is 0, then you just remove those zero pairs. Let's have more examples. Add 2x squared plus 6x plus 5 and 3x squared minus 2x minus 1. Let's visualize them. There are 2x squareds, there are 6x's, and 5 constants, and this is 3x squared. Now you have here minus 2x, so think of this as negative 2x, so it should be red, and you have minus 1, that should also be red. Then after that, we can simplify, combine like terms. So these are all x squared, and there are 5 of them, so we write that as 5x squared. For the variable x, we have x and negative x and negative x. We can eliminate these zero pairs, so remove them. What's left is we have 4x's representing 6x minus 2x, so this is the result. And there's also another zero pair here, 1 and negative 1 becomes 0, so 5 minus 1 equals 4. So therefore, this is now the answer. 2x squared plus 6x plus 5 plus 3x squared minus 2x minus 1 would now be equal to this trinomial 5x squared plus 4x plus 4. Now, what happens if we no longer have those manipulatives? How are we going to find the sum of this? The idea is line up all those like terms. We have here x squared, we have here x squared. These are like terms. The same here, x and constant and constant. Then just combine them. 2x squared plus 3x squared equals 5x squared. 6x minus 2x is 4x, and 5 minus 1 is 4. That is the same as the answer we arrived previously. This red one was arrived at using visualization, and this one is now arrived at using just algebraic manipulation. That is now what we call as scaffolded mathematics. We start with some visual help, and once we understood the concept, we can eliminate that scaffolding, that visualization, that manipulatives, so that you can perform the more abstract operations. Next, let's now practice without these manipulatives. Let's say we have 4k to the fourth plus 14 plus 4k squared plus negative 3k to the fourth minus 14k squared minus 8, and we want to find the sum. Again, only like terms can be added or subtracted, so let's identify the like terms. 4k to the fourth and negative 3k to the fourth are like terms. Their variables are k to the fourth, k to the fourth. Positive 4k squared and negative 14k squared are also like terms because the variable part, k to the second, is the same here, k squared. And all constants are like terms also. So we are going to combine the like terms. So they are now grouped together by shapes. The circles are like terms, the rectangles are like terms, and the hexagons are also like terms. So 4k to the fourth minus 3k to the fourth is equal to 1k to the fourth. 4k squared minus 14k squared is negative 10k squared. You can think of this as you have an income of 4, but your expenses is 14. So you are still negative, that is negative 10. And then copy the common literal coefficients k squared. Then 14 minus 8 is equal to 6. This is now our answer. Let's have another example. Let's say we have subtraction. 4k to the fourth plus 14 plus 4k squared minus negative 3k to the fourth plus 14k squared minus 8. Now, when this is subtraction, we do not invent another rule. Still, the rule is only like terms can be added or subtracted. There is only an additional step that you are going to perform. And that additional step is to convert this problem into addition, because by definition, we know that subtraction is just the addition of the additive inverse. So if we make this subtraction into addition, we are going to get the additive inverses of all these terms inside this parenthesis. So this negative becomes positive, this positive becomes negative, and this negative becomes positive. So this is now how this problem looks like. We copy all the terms preceded by plus sign, no problem about that. But when you have a negative sign turned to positive, change the sign of all those terms inside the parenthesis. So this is important, so let's look at this again. Originally it was minus, this is now positive. Originally it's positive, this is now minus. Originally it was minus, it is now plus. That is what we mean by subtraction as adding the additive inverse. From subtraction, that becomes addition by additive inverses of all these terms inside the parenthesis. And I would like to keep on emphasizing this. So once we perform that added step of converting from subtraction to addition, then we can identify the like terms. These are the like terms grouped according to shapes. And perform now the simplification. 4k to the fourth plus 3k to the fourth is equal to 7k to the fourth. 4k squared minus 14k squared is equal to negative 10k squared. And positive 14 plus 8 is equal to 22. And therefore, this is now our final answer. Notice that it's still the same procedure, only that we have to convert from subtraction to addition by using the definition that subtraction is adding the additive inverse. Next, let's look at some application of this. Let's say this is the problem. A rectangular garden has one side with a length of x plus 7 and another with a length of 2x plus 3. Find the perimeter of the garden. So what is a perimeter? A perimeter is the distance around the figure. So if this is x plus 7, this is also x plus 7 because opposite sides of a rectangle are equal. If this is 2x plus 3, the opposite side must be the same measurement because opposite sides are equal. And therefore, to find the perimeter, in the book, usually they have this formula. Perimeter is equal to 2L plus 2W because there are two lengths of the same measurements and two widths of the same measurements. But since we are still in addition and subtraction of polynomials, let's not perform the multiplication yet. Let's do the addition first. So we are going to add all these four sides this way. And this is application of addition of polynomials. We add all the like terms. 2x plus 1x plus 2x plus 1x is 6x, and add all the constants. So the perimeter is 6x plus 20. Now, how about if we use that formula? P is equal to 2L plus 2W. Let's see what happens. You have 2 times our length 2x plus 3 plus 2 times our width of x plus 7. Now here you have a monomial times a binomial. We are going to perform what we call as the distributive property. Here, you distribute the monomial factor to the binomial factor. So 2 times 2x is equal to 4x. Then distribute this 2 again, multiplied to positive 3. So 2 times 3 is equal to 6. Then go to the next monomial factor, multiplied 2x to get 2x. And 2 times 7 is equal to 14. So what happens is we distribute this 2 to the binomial and distribute this 2 again to the other binomial. The result would be these 4 terms. Then rearrange to combine like terms. So 4x plus 2x is equal to 6x. 6 plus 14 is equal to 20. You will get the same result as the previous one. So in mathematics, as long as you do not violate any rule, you will arrive at the same answer even if you have different ways of solving the problem. So next, let's proceed to multiplication of polynomials. Here we are going to look at different cases. The first case is a monomial times another monomial. Second is a monomial times a multinomial. And third, a multinomial times another multinomial. And we also have special cases like squaring a binomial. So let's look at the first case, a monomial times a monomial. An example of that would be 2x times 3x. 2x is a monomial, 3x is also another monomial. Visually, we said 2x is represented like this, and 3x would be 3 x's put together side by side like this, from one end to the other end. Then to multiply means to find the area of a rectangle with a side length of 3x and a width of 2x. So here we are multiplying this 2x times 3x. We can also interchange. You can put here the 3x and the 2x there. It doesn't matter. Multiplication is commutative. We can rearrange the order of factors and the product is not affected. So what's the area now of this rectangle? Let's tessellate it with x squared. Why x squared? Because x times x is x squared. So all of these are of dimension x times x. The area is x squared. And there are how many x squared are there all in all? There are 6. And therefore, we now say that the product of 2x times 3x is equal to 6x squared. 1, 2, 3, 4, 5, 6. Visually, you can see this 6x squared. But if you are going to recall the law of exponent, when you multiply numbers in exponential form with the same bases, here the base is x and x, you copy the common base and you add the exponent. What's the exponent of x? That's 1. Here it's also 1. 1 plus 1 is equal to this 2. So notice how consistent the rules are with the visual interpretation of these algebraic expressions. Next problem. Let's say we have 5x y to the 4th times 6x to the 5th y to the 4th. Again, don't forget this law of exponent number 1. This is the product rule of exponents. So how do we multiply this? The idea is you multiply the numerical coefficients 5 and 6 to get this, and 5 times 6 is 30. Then take this variable x and look for another literal coefficients with variable x. You have here x to the 5th and x. The exponent here is 1, so copy the common variable x and you add the exponent 1 plus 5 to get the 6. Then go to the y. The exponent is 4. Here, the exponent is 4. You add 4 plus 4, and that's 8. So you now have here y to the 8. That's how you multiply a monomial times another monomial. Let's go to case number 2. A monomial times a multinomial. Here's an example. X times x plus 2. So the first factor is x. The second factor is x plus 2. This plus sign separates the term. That means this x is one term and this 2 is another term. The boundary of each term is this plus or minus sign. So let's visualize this now. X is visualized as like this, and x plus 2 would be an x and 2 units. So this length is the x plus 2 and this length is the x. And this is now how we multiply x times x plus 2. We form here a rectangle and cover that area with our other manipulatives. So you have here x squared, you have here x, and you have here x. How do we know that this is x squared? You have a side length of x and a side length of x, and x times x is x squared. How do we know this is x? You have here a length of x and a width of 1. So 1 times x is x, similar here. Now, we now say that the product of x times x plus 2 is now x squared plus 2x, because there are 2 x's here combined. Now, if we are going to perform the distributive property of multiplication or addition, it's like this. X times x to get this x squared, then distribute again x to 2, so x times 2 would now be 2x, and therefore, we can also arrive at the product x squared plus 2x even without this manipulative by performing the distributive property of multiplication over addition. Distribute x to the first term to get x squared, and distribute x again to 2 to get 2x. Since this can no longer be combined because they are unlike terms, then that's already our final answer. So the answer is x squared plus 2x. So this is now our final answer. Now let's have another example. X times the quantity x plus y plus 2. Again, we can visualize it like this. The length is x plus y plus 2 and the width is x. Again, we can use manipulatives to visualize them like this. The width is x and the length is x plus y plus 2. Then we form this rectangle. What's the area of that? We have x squared, xy, and 2 x's. So we have x squared plus xy plus 2x for the product of x times the quantity x plus y plus 2. Now, if you're going to perform the distributive property of multiplication over addition, x times x is x squared, x times y is equal to xy, and x times 2 is 2x. And that is now our final answer. Let's solve some exercises. 3x squared times the quantity 4x minus 8. What's the product? You can pause the video and see if you can solve this. Now let's do this together. Perform the distribution. 3x squared times 4x is equal to 12x cubed. 3x squared multiplied to negative 8, that becomes negative 24x squared. And that is letter B. Next problem. 6a times the quantity 3a minus 8. Again, perform the distribution. 6a times 3a is equal to 18a squared. 6a times negative 8, that is equal to negative 48a. And so our answer is letter D, 18a squared minus 48a. Next problem. 4 times the quantity 2x squared plus x minus 6. So again, distribute. 4 times 2x squared equals 8x squared. 4 times x is equal to 4x. And 4 times negative 6 equals negative 24. And that is letter A. And one more, 7n times the quantity 2n squared minus 6n plus 7. So again, distribute. 7n times 2n squared is 14n cubed. 7n times negative 6n is equal to negative 42n squared. 7n times 7 is, of course, 49n. And that is letter A. Now, let's proceed to the third case. A multinomial times another multinomial. So here is an example. A plus B is a multinomial, and C plus D is also another multinomial. When we say multinomial, it's a polynomial with 2 or more terms. I said the boundary is this plus sign. So this is one term, this is another term. The same thing here, this is the boundary between terms. C is a term, D is a term. So there are 2 terms here, and there are 2 terms also here. And we would like to multiply a binomial times another binomial. So, how do we multiply this? This is what we're going to do. Let's visualize them. And again, form a rectangle, and the area is the product. So what is the area of this part here? That would be A times C. So that's AC. Then, let's take a look at this area. This is A, and that's D. So the area is AD. This is B, and this is C. So this area here would be BC. And the remaining part would be, this is D, this is B, that is BG. So, the product therefore would be these 4 rectangles, and that is AC plus AD plus BC plus BD. If there are terms that we can combine, then let's proceed to combine them. But in this case, there's nothing more that we can do here. They are unlike terms already. Now, if you're going to use the distributive property, A times C is this AC, then A times D would be this one, then B times C would be this BC, and B times D equals BD. When you multiply binomial times a binomial, there's a code called FOIL method. In my experience, I oftentimes forget to distribute some terms, so I always use the tabular or the grid method. The grid method is like this. I listed down A plus B here, and C plus D at the top. Then I perform the multiplication pair by pair. And therefore, here is now the result. Notice that A times C is this, A times this, B times C is this, and B times this one. And you still arrive at the same result. The advantage of this is you can easily visually notice if you forget something because there would be a hole in your graph. But in the distribution, sometimes I forget to distribute some terms. Now let's solve this problem. The quantity 4p minus 5 times the quantity 2p plus 1. So again, let's use the grid method. 4p minus 5 at the left and 2p plus 1 at the top. And perform the multiplication box by box, pair by pair. And the final answer would be this 8p squared. Let's put it there. Notice that negative 10p and positive 4p are like terms. So we can combine them to negative 6p and copy minus 5. That is now our answer. Let's have another example. Again, let's use the tabular method. 3k minus 7 at the left and 7k plus 4 at the top. Fill the boxes by multiplying the factors pair by pair. So 3k times 7k is 21k squared. For this box, 3k times 4 is 12k. For this box, negative 7 times 7k is negative 49k. And lastly, negative 7 times 4 is negative 28. Then, combine like terms. Copy 21k squared. Then minus 49k plus 12k, they are like terms that we can combine to negative 37k and copy minus 28. And we now have the answer, which is letter A. Notice that the tabular method is easier to use, especially when you are a visual learner like me. Next problem. The quantity 7n minus 6 times the quantity 6n minus 1. So again, perform the multiplication using this table. 7n times 6n is 42n squared. 7n times negative 1 is negative 7n. Negative 6 times 6n is negative 36n. And negative 6 times another negative 1 is positive 6. Final answer, copy 42n squared. Then combine these like terms to negative 43n and copy 6. And we now have our answer, which is letter D. Another example. This time you have a binomial times a trinomial, but still the process is the same. So, multiply pair by pair. And in this case, you have 6 partial products. Then once you have those partial products, combine like terms. There's nothing like 20k to the third, so just copy it. But negative 12k squared and negative 15k squared are like terms, combined to negative 27k squared. The same with 9k and 20k that can be added to 29k and copy minus 12. And that is now the answer, which is letter B. With the tabular method, it's very clear. If you forget something, there's a hole in your table. Next, we have here a trinomial times another trinomial. So the same procedure. Multiply them pair by pair. And once you have these 9 partial products, look for like terms. So we copy 5b to the fourth. There's nothing like it. Usually diagonally, that's where you can find the like terms. Negative 2b cubed minus 10b cubed is negative 12b cubed. Here, there are 3 like terms. 4b squared plus 4b squared plus 5b squared, that's equal to 13b squared. And then, minus 8b minus 2b is equal to minus 10b, and copy plus 4. That is now our final answer. And for your practice exercises, you can work on these 2 homework problems. So you can try these 2 items yourself. And the answer to that would be number 6 is letter D and number 7 is letter B. Now let's talk about the special products of polynomials. These are multiplication of polynomials that are easier to perform because there's pattern. That's why we call them as special products. The first one is the square of a binomial connected by a plus sign. The second is the square of a binomial connected by a minus sign. And the third one is the product of the sum and difference of 2 numbers. These 2 numbers, A and B, are the same, only that one is plus, the other is minus. So it's important that we understand this because this is a recurring lesson when you perform computations in higher mathematics. So let's visualize first the first case, the square of the binomial A plus B. So how do we visualize A plus B? It's like this, and this is the same A plus B. The product would be this one. Let's find the area of the square with a side length of A plus B and another A plus B here. So this part here would be A by A, so that would be A squared. Now, this part here would be B by B, so that's B squared. And this part here, it would be A times B, so it's AB. The same here, it's AB also. So, adding all these partial products resulted to these 4 areas, A squared plus 2AB plus B squared, because AB plus AB is 2AB. And this is now the formula which we call as the square of a binomial. When you square a binomial, just square the first term, get twice the product of the first and the second term. So the product of the first and the second term is AB and double it to get 2AB and square the last term, that would be B squared, which is now this B squared here. Let's have an application of this. So for example, you have the square of P plus 7. So let me show you how this formula is applied. We first copy the problem. What is the first term? In here, our A would be this P, our B would be this 7. So follow this. A squared means you square P. You have P squared. Next is 2AB. So write the 2 and multiply P times 7, and that's the result. Then plus B squared. Our B is 7, so plus 7 squared. Then simplify. Copy P squared. 2 times 7 is 14, so we have 14P, and then 49, because 7 squared is 49. That is now our answer, and you can also arrive at this mentally. Just square P to get P squared, multiply 7 times P to get 7P and double it to 14P, and then square 7 to get 49. That is the reason why we call this as the special product. Next, in here, we can automatically eliminate option A and option B because for the square of a binomial like this, we always expect 3 terms for the answer. So it's either C or B. Let's copy the problem. So you square the first term. 3 squared is 9B squared, so you have 9B squared. Then multiply 3B times 5 and then double it. 3 times 5 is 15. Then copy B, 15B, and double that to get 30B. And then square 5 to get 25. So the answer is letter B. Next, we have now here the square of a binomial, but the sign is minus. This is a little hard to visualize. So AB is visualized like this. You have this blue rectangle with a dimension of A. Then you are going to subtract B. So you are going to cut this portion. So this is now A minus B. That means we need to remove this part. That is the meaning of minus B. Take this away. Remove this. Cut this. So this is A minus B. Then we have another A minus B. So we have the same representation. That means we need to remove this part also. So to multiply now the quantity A minus B times the quantity A minus B, we are only after this smaller square. We want to remove this extra space. But since when you operate on this, what's given is A and B, then we start by looking at the area of A by A again, and that is A squared. And then we identify A minus B squared. This is A minus B squared. The shaded part is A minus B squared. And to get to this area, we need to remove all of this. We need to remove this, we need to remove this, and we need to remove this. And how do we do that? Notice that we said this is B and this is also B here. So this area here would be, the entire length is A, the width here is B, so that is AB. So we subtract AB minus AB. We already remove this entire part here. Then we need to remove this also. Now, if we put another AB, notice that this part here is counted twice because there is an overlap. That's why if we subtract minus AB here, we have to return this overlap. And what is this overlap? This is B times B, which is B squared. We need to return that. That's why we have plus B squared. And by doing so, what's left would only be the square of A minus B. We already remove these outside areas. And simplifying this, we have A squared minus 2AB plus B squared, which is now the formula for the square of a binomial connected by a minus sign. Now, let's apply this formula. So again, let's copy the formula and let's copy the problem. Here, our A is 5B, our B is 7. So the formula says you square 5B to get 25B squared, then copy the minus sign, and then 2AB. So 2 times the product of 5B and 7. Notice that the minus is already here. Plus B squared. So 7 squared. Don't confuse with the sign. So this minus sign is here. So you think of your A as 5B. You think of your B as positive 7. Just put the sign here. So for 2AB, it's 2 times 5B times 7. For B squared, it's 7 squared. Then all the rest is just simplification. And so our final answer would be 25B squared minus 70B plus 49, which is letter D. Now let's proceed to the third case, the product of the sum and difference of two numbers. And this is equal to A squared minus B squared. Now to visualize this, it's easier that we start our visualization with this right side. So we know A squared, it's a square with a side length of A. So this red square is our A squared. Now B squared would be a square with a side length of b. So this part here is b squared. Now what we want to do is remove this b squared from a squared. So we are going to subtract. But before we split this figure, let's identify first the measurements. So this length of the big square is a. The side length of the small square is b. So this part here would be the difference between a and b. So that is a minus b. Also, this part here would be a minus b. And now we are ready to subtract this b squared. Notice that we have an a squared and we want to subtract b squared. So let's remove the b squared. This is now how this looks like. This L-shaped area is the a squared minus b squared. Literally, a square of dimension a squared subtracted by a square of dimension b squared. So what is now the area of this remaining red shaped figure? This is what we are going to do. We are going to separate the components, and so we have this composite figure. And then let's form a rectangle by joining these three parts together like this. If you are using a paper, you can just have two parts that you put together like this. You don't have to cut into three. I just show it in this animation. What is the area of this red rectangle? Well, we need to know what is this length here. It's a minus b. And what is the length here? That is a plus b. So therefore, a plus b is this part. You have a plus b here. And the a minus b is this part, which is now this a minus b here. So the product of a plus b, which is this length, times a minus b, which is this length, would now be the combined area, which we know was a squared minus b squared. And that is the visual proof of this difference of two squares. For factoring, you start with the right side and you go back to the factors. For special product, you start with a product that look like this, and you can write that as difference of two squares. So this is now what we call as the special product, the product of the sum and difference of two numbers that is equal to the difference of two squares. So let's see some application of this. So again, we need to recognize that the given problem is similar in form as this formula. So the first term is 8k, they're the same. The second terms are 7 and 7. One is plus, the other is minus. That is exactly the meaning of this. So let's copy the problem. Then the product would be, take the square of the first term. The square of 8k is 64k squared, minus is copied, and get the square of the second term, 7 squared. It doesn't matter whether the first factor is the minus, the second factor is the plus, as long as you have the product of the sum and difference of exactly two numbers. Here, the two numbers are 8k and 7. One is expressed as plus, the other is expressed as minus. So simplifying, this is equal to 64k squared minus 49, this is letter B. Next problem. So again, write the formula and write the given. What are the two numbers? It's 7x to the third and 8. So following this formula, that is equal to the square of 7x cubed, which is 49x to the sixth. Copy the minus sign. And then the square of b is the square of this 8, which is 64. So here is now our final answer. And that is letter D. Here are some practice exercises with answers that you can practice with. You can just pause the video and proceed once you are already done with these practice exercises. And here's another one. This is now medium in difficulty part, and this is the hard part. So let's proceed now to the next lesson. Now let's talk about division of polynomials. For division of polynomials, there are three cases. And basically, these are three cases similar to the multiplication of polynomials. So let's start with the first one. Monomial by a monomial. Here we'll be using this law of exponent number 2 most of the time. And under this quotient law of exponent, there are three cases. One is when the exponent in the numerator is greater than the exponent in the denominator. The other is when the exponent in the denominator is greater than the numerator. That is when we have this negative exponent. And the third case is when the exponent in the numerator and the denominator are equal. In that case, we have this zero exponent. So let's continue. Here is an example of a monomial divided by a monomial. As is, this is not a polynomial because there is a variable in the denominator. But what we are doing here is, we have here a monomial, and we would like to divide by another monomial. So think of this as dividing monomials. And how do we divide this? First is, we need to group together those factors with the same variables. For example here, x and x, I lined up them together. I also lined up together those factors with variable y. And the numerical coefficients are also lined up together. Then simplify. 28 divided by 49 is equal to 4 over 7 in lowest term. X to the 5th divided by x to the 9th, we are going to apply law of exponent number 2. So we copy the common base and subtract 5 minus 9. That resulted to a negative exponent. And when the exponent is negative, we can write that in the denominator with positive exponent. So we now have x to the 4th, but in the denominator. Now y to the 14th divided by y to the 12th is y squared. And this is now the result. So the final answer would be 4y squared over 7x to the 4th. Now let's take a case when we have a monomial divisor and a multinomial numerator. So let's say we have 4x to the 3rd plus 5x squared plus 3x all divided by 9x. So the numerator is a multinomial and the denominator here is a monomial. So how do we find the answer to this problem? Here, each one of these terms in the numerator will be divided by 9x. So think of this as distributing 1 over 9x to each of the terms in the numerator. And there are how many terms all in all in the numerator? We have 1, we have 2, we have 3. Always think of the plus or the minus sign as the separator of terms. So this is now what will happen. Each one of these terms in the numerator is now divided by the monomial denominator. Then the rest is just simplifying this. 4x cubed divided by 9x is 4x squared over 9 because we subtract the exponent 3 minus the exponent 1 here to get x squared. 5x squared divided by 9x is equal to 5x over 9. So you can think of this like this. X squared divided by x is x to the 1st. That's why you have this x here. Then here, x divided by itself is 1. So what's left is the lowest term of 3 over 9, which is 1/3. Notice that our answer still consists of 3 terms. So this is now our final answer, and that is letter B. Next problem. 40n to the 4th plus 5n cubed plus 5n squared, all divided by 10n squared. Again, this is a multinomial divided by a monomial. So, again, we are going to divide each of the terms of the numerator by the monomial denominator 10n squared. We now have 3 terms here all in all. Then perform the division applying law of exponent number 2. The first term becomes 4n squared because 40 divided by 10 is 4. N to the 4th divided by n squared is n squared. We subtract the exponent 4 minus 2 to get this 2. Here, 5 over 10 is 1/2 in lowest term. N to the 3rd divided by n squared is n. So the numerator is 1n, the denominator is 2, but we do not write that 1 anymore. And here, lowest term of 5 over 10 is 1/2 again. Then this n squared and n squared, when divided, would be equal to 1. So the answer is 1/2 for the 3rd term. And this is now our answer, which is letter B, this one. Next problem. X squared plus 5x minus 2 divided by x minus 1. This time we now have a multinomial divided by another multinomial. So this is case number 3 now. So in here, this is what we are going to do. We are going to perform what we call as the long division. In the long division, this is the procedure. This was the numerator, this was the denominator, this is the dividend, this is the divisor. So to find the quotient, divide the first term of the dividend by the first term of the divisor. So x squared divided by x is equal to x. Then x times x is equal to x squared. Then x times -1 equals negative x. So we distribute this x to this binomial. Then subtract. X minus x is 0. This becomes 5x minus negative, so this becomes plus. So 5x plus x is equal to 6x, and bring down -2. Then repeat the process. The first term here divided by this x is positive 6, and then distribute 6 to x minus 1 to get 6x minus 6, and then subtract. Then this becomes minus 6x. Change the sign here to become plus 6. So -2 plus 6 is equal to positive 4. This 4 now is the remainder, and we write the remainder over the divisor. So plus 4 over the divisor x minus 1, and that's the answer. And that must be letter A. And another problem on long division, let's say we have x squared minus 12x plus 30 divided by x minus 8. So again, let's perform the long division method. There's also another method called synthetic division, but our video for that would be separate from this. So again, this x squared divided by x resulted to x, and then distribute x to the divisor x minus 8 to get x squared minus 8x. Then subtract. This becomes minus, this becomes plus, and then proceed to addition. X squared plus negative x squared is 0. Negative 12x plus 8x is negative 4x. Then bring down plus 30. Then again, this first term divided by x is negative 4. Then distribute negative 4 to x minus 8 to get negative 4x plus 32. And then change the sign here, change the sign here. So 30 plus negative 32 is equal to negative 2. And that is our remainder. So minus 2 over the divisor x minus 8. And that is letter A. Next problem. This time we have 4 terms in the numerator, and we have 2 terms in the denominator. So prepare for long division. 2b cubed divided by 2b is b squared. Then distribute b squared to arrive at this. Then change the sign, and proceed to addition. This becomes 0. Minus 13b squared plus 3b squared is minus 10b squared. Bring down 23b. Then divide. This first term divided by 2b is minus 5b. Then distribute minus 5b to this binomial to get minus 10b squared plus 15b. Then change the sign, and proceed to addition. This is 0. 23b plus negative 15b is equal to 8b. Then bring down minus 8. Then repeat the process. Distribute 4 to 2b minus 3 to get this. And then change the sign to minus and proceed to addition. Negative 8 plus 12 is positive 4. And that is the remainder. And so, our answer is letter B. So at this point, I believe we have covered a lot about polynomials, from its definition to its visualization to operations with polynomials. There are other topics that you might still need that's not in this video, like the synthetic division, but we will reserve that for the next videos. So again, thank you very much, and good luck to those who are going to take their board exams. Good luck to those students who are taking their exams. My name is Lando ASISTEN, and I would like to invite you to please subscribe, like, and share our videos. We are making this comprehensive, scaffolded visual mathematics because we believe this is the way for you to learn mathematics better. Again, this is Lando ASISTEN, Filipino, Bicolano. Thank you very much, and we hope to see you again in our next video. Bye for now.